Welcome to Calculus. Today we will investigate finding limits at infinity of rational and radical functions, focusing on analytical strategies when direct substitution fails. Let's take a look at 5 examples. Our first example is the limit as x approaches infinity of the rational function 2x squared over x squared plus 4. Up until now, we've been dealing with limits as x approaches finite values, either from the left and from the right, or simply from one side, from the left or from the right. So what's new for us with these 5 examples is now we're headed towards either positive infinity or negative infinity. And our challenge when we do that is that direct substitution really doesn't yield much information. Direct substitution works best when I'm approaching finite x values. When I'm approaching an infinite value, however, direct substitution doesn't really apply a whole lot. And we can see that if we try it with this first example. So if I took the function and instead of x put in infinity and then square it, and say that that's over infinity squared plus 4, I really have no way of evaluating that. And so what we have to do is come up with some algebraic strategies that will, in a way, trap the infinity in a place where I can evaluate it. So I'm going to get rid of that direct substitution strategy to begin with. And I want to enlarge this, so I'm going to rewrite the limit. It's the limit as x approaches infinity of 2x squared over x squared plus 4. Now, my strategy when I do this is I really want to get my x values in some single denominator position. So what I'm going to do with this one is I want to multiply through a fraction 1 over my highest x power in the denominator, really. That's kind of where I'm focusing my attention. So I see my highest x power in the denominator is x squared. So what I'm going to choose to multiply through both my numerator and denominator is 1 over that high power in the denominator, x squared. Now I can get away with that if I do it both in numerator and denominator. This complex fraction in red, 1 over x squared divided by 1 over x squared, it has the value of 1. So I'm not really incorporating anything new algebraically. I'm just rewriting the fraction. So let's multiply that through. So this would equal now the limit as x approaches infinity of, in my numerator, 2x squared over, if I was multiplying 1 over x squared, the 1 would hit the 2x squared and give it back to us itself over simply x squared. So that x squared shows up in the denominator. All right, we'll do the same with this x squared plus 4, and I'm going to distribute it to each of the terms. So it's going to be x squared over x squared. So that's that first distribution. Second one's going to be plus 4 over x squared. And once I get those written, I see that I've got some cancellations that I can make. And that really is critical for us. We need those cancellations. So at that point now, that equals the limit as x approaches infinity. In my numerator, the x squareds cancel, and so all I'm left with is the constant 2. In the denominator, the first terms cancel the x squared, so that's just 1. And then I'm going to leave plus 4 over x squared. So you can see by this strategy, I've in a way trapped the x squared in the denominator of a term in my denominator. Well, at this point, we need to apply some of our analytical reasoning strategies. So I'm going to do something that kind of approximates direct substitution here, even though really I can't substitute infinity in for a variable. So I'm going to write this now without the limit. It's 2 over 1 plus 4 over, and I'm going to pretend as if I'm substituting in infinity and then squaring it. So the 2 in the numerator, the 1 in the denominator, those aren't changed. What is changed is this 4 over infinity squared, and we have to think, if I'm taking a number, in this case 4, and dividing it by an extraordinarily large number, it's going to get closer and closer and closer to 0. And so what I would say is that this is really equal to 2 over 1 plus 0, which is just 2 over 1, or simply 2. And that is the value of our limit. Let's take a look at a second example. So this example has the limit as x approaches negative infinity, so we can approach the negative side of things, of the function negative x squared over x plus 1. So what I notice in the actual function itself, the high powers in the numerator, there's a difference in terms of my high powers on x. See how the x in the denominator is to the power of 1. So when I think about how to apply that same strategy we just used, I need to really focus on the denominator. So I'm going to say again, rewriting this in a larger format. So limit as x approaches negative infinity of negative x squared over x plus 1. So I want to multiply again by something that's going to trap the x, the infinity, in the denominator of one of these terms down below. So what I'm going to multiply by is not 1 over x squared, but simply 1 over x. I'm taking my cube from this term in the denominator. And like we did, I'm going to repeat that above, and then I want to distribute that through. My next statement would look like the limit as x approaches negative infinity of negative x squared in my numerator over simply x, make sure I put squared, over, and then again I'm going to distribute this 1 over x to each term in my denominator, so that's x over x, we see some cancellations forming, plus 1 over x. So let's make good on those cancellations. I see that in my numerator, one of the x's is going to cancel. All right. So then in my denominator, I'm going to cancel both of those x's, and then I'm going to leave 1 over x. So my next step is the limit as x approaches negative infinity of x over 1 plus 1 over x. So at that point, I'm ready to do the direct substitution. And again, it's not something that I can directly evaluate. I'm going to have to apply some just analytical reasoning, since negative infinity really doesn't calculate well. I see I forgot my negative out front, so make sure to put that. So this becomes negative. My limit says I'm approaching negative infinity, so I'm going to substitute that for x in the numerator over 1 plus 1 over negative infinity. So then I got to interpret some stuff. First, in my numerator, the negative doubled there is going to become positive. So my numerator I can rewrite as just simply positive infinity. And then for denominator, the 1 stays. And just like we saw in our first example, this 1 over negative infinity, it's the same as if I was dividing by positive infinity. It's just approaching the value from the other side. 1 divided by an extraordinarily large number, positive or negative, is going to tend towards 0. So that's 1 plus 0. 1 plus 0 is 1. Infinity divided by 1 is infinity, and that is where we're headed for this limit. So 2 examples there of rational functions. Let's take a look at one of these that involves a radical. So for this one, I've got the limit as x approaches infinity of the cube root of x squared plus 3 over 4x squared plus 5. So notice the whole rational function is inside that cube root. So again, I want to apply the same strategy, but somehow I have to sneak in a term under that cube root. So I'm going to rewrite that limit again, just so it's larger format. Limit as x approaches infinity of the cube root x squared plus 3 over 4x squared plus 5. So my attention initially is drawn to this x squared, which means I want to create denominators of x squared. So I could think I'm going to multiply by 1 over x squared over 1 over x squared. But the problem is I also have to, in some way, reconcile with the cube root. So instead of just multiplying 1 over x squared, what I need over here is to make just an observation that if I'm going to get an x squared under a cube root, so I'm going to write cube root of x squared, which is how this is going to appear on the interior of that radical. Another way that I can write that is as x to the power of 2/3. So instead of multiplying by 1 over x squared over 1 over x squared, I need to modify that to include this taking into account the cube root. So I'm going to multiply by 1 over x to the power of 2/3 times 1 over x to the power of 2/3. So that's going to pass inside the radical, and as it passes in, it's going to become effectively over x to the power of 2. So let's rewrite that. This will now become the limit as x approaches infinity of the cube root of x squared. Now, as it passes in, because of the way that that x to the 1 over x to the power of 2/3 interacts with the cube root, it becomes simply x squared, really 1 over x squared. So again, what we're seeing is we get that advantage of a cancellation. And then what we're seeing is we're also trapping different powers of x squared in the denominators. So that's my numerator. And my denominator is going to be 4x squared over x squared plus 5 over x squared. Now, at that point, what I want to do is make those cancellations. So I'm going to cancel any x squared terms. So I've got one of each in my numerator and denominator. And that then will equal the limit as x approaches infinity of the cube root of, in my numerator now, 1 plus 3 over x squared. In denominator, 4 plus 5 over x squared. And now we're ready to approximate direct substitution. So then I'm going to say this is the, let me back up because I don't need the limit statement, the cube root of 1 plus 3 over infinity squared. And then that's all over 4 plus 5 over infinity squared. So just thinking about what these two terms that are over infinity squared are going to become, as I divide a single modest number, in this case 3 or 5, by an enormous number, infinity squared, that becomes basically 0. And so what I'm left with by applying that analytical reasoning is that this is equal to the cube root of 1 over 4. Well, let's simplify that statement because we really want to make sure to rationalize the denominator. So what I need to do here is apply that cube root to the numerator separately and the denominator. So that's cube root of 1 over cube root of 4. And cube root of 1 is 1. Cube root of 4. So then I need to do that rationalization. So I'm going to do the cube root. So I do need to have it, to make this simply 4 in the denominator, I need to have 4 cubed under the cube root. So this is going to be cube root of 4 squared, or 16. Cube root of 16. So when I multiply that out, that's going to be the cube root of 16 in my numerator over, I can multiply 4 times 16, that would be the cube root of 64. And that is 4. There's one more simplification we can do with this cube root of 16. So keep in mind 16 is 8 times 2, so that's the cube root of 8 times 2 over 4. Cube root of 8 is 2, so it's 2 times cube root 2 over 4, and that reduces down to the cube root of 2 over 2. So a little bit of algebra to rationalize the denominator of our final limit, but we do get the cube root of 2 over 2. So we can use that same strategy of trapping the infinity in the denominator to make it go to 0 of just a few terms. Let's take a look at when the radical is not over the whole function, but simply in the denominator. So here's the limit as x approaches infinity of the fraction 3x plus 2 over the square root of x squared plus 1. So we'll write this again. Our strategy is going to be very similar. So I'll write it just so we can see it larger format. Limit as x approaches infinity of 3x plus 2 over the square root of x squared plus 1. So again, I want to multiply a couple factors, 1 over something, to both the numerator and the denominator. So again, I got to think what that's going to be. So I need to make an observation that the square root of x squared, because that's really what I want to distribute into that lower value, is x. So I'm going to multiply by 1 over x and 1 over x. So let's make those distributions. So this is now the limit as x approaches infinity of 3x divided by x plus 2 divided by x. And you see those two distributions. So I'm distributing 1 over x to each term in my numerator. Same in the denominator, and it is passing into the radical. So now I'm going to represent that 1 over x as 1 over x squared. So this is now the square root of x squared over x squared plus 1 over x squared. And at that point, we're ready to make some cancellations. So my x terms above cancel, x squared terms within the radical cancel, and we're ready to write that simplified form and then make some approximations of a direct substitution with infinity. So this is the limit as x approaches infinity of simply 3 plus 2 over x. So you can see I've trapped the x under the 2 there. And then in denominator, square root of 1 plus 1 over x squared. Same phenomenon down there. I've trapped that x squared under the 1. So now I'm going to do that approximation of direct substitution. So this is 3 plus 2 over infinity. Notice I've dropped my limit expression because I'm substituting over square root of 1 plus 1 over infinity squared. We can use now our analytical reasoning to decide what's going to happen to these fractions, 2 over infinity and 1 over infinity squared. It's the same idea that we've been using. If I divide a modest number, 2 or 1, by an extraordinarily large number, infinity or infinity squared, that value is going to tend towards 0. So my final expression here is going to be in numerator 3 plus 0 over the square root of 1 plus 0, which is 3 over square root of 1 plus 0 is 1, square root of 1 is 1, 3 divided by 1 is 3. And that gives us our limit here for this function as x approaches infinity. Let's take a look at one final example here where we've got the radical in the numerator. So here I've got the limit as x approaches negative infinity of the square root of 2x squared plus 2 over 3x plus 3. I will rewrite that again so we see it larger. Limit as x approaches negative infinity. So this negative infinity, we've got to treat that carefully so that we mind our sign in the final limit value. Of the square root of 2x squared plus 2 all over 3x plus 3. So I am going to multiply by those two fractions, 1 over, 1 over. So we need to decide what that denominator in the red will be. So I'm going into the square root, and I want it to be 1 over something x squared when it enters square root. So again, I'm going to note that the square root of x squared equals x. But I do notice that I'm looking at the limit as x approaches negative infinity. So I need to make sure that my square here in the radical isn't going to cancel that value. So I'm going to put a negative out front, which means when I multiply stuff through, I need to put a negative out front of my limit expression. I'm going to save it for my next. Actually, I'm going to leave it right there. So I do need to incorporate that negative in the limit. Well, that helps me with this value. So it's 1 over x times over 1 over x, and I'm going to multiply those through the radical. So let's do that. That's now the limit as x approaches negative infinity. Got that negative there since we are headed to negative infinity of the square root of 2x squared. So we're going to see that distribution over x squared. So remember, as 1 over x goes into the square root, it becomes x squared plus 2 over x squared all over 3x, also now divided by just x. So I'm not in the radical now. And so I don't have to scale that up to x squared. So 3x over x plus 3 over x. And at this point, I'm ready to do the cancellations. I'm going to cancel my x squared terms. And again, I've trapped x squared under the 2. In the denominator, I'll cancel my x terms, and I've trapped the x under the 3. So then my next expression is the limit as x approaches negative infinity of negative square root of 2 plus 2 over x squared over 3 plus 3 over x. Ready to approximate direct substitution now. Negative square root 2 plus 2 over, instead of x, I'm going to write infinity squared, all divided by 3 plus 3 over infinity. And with those two terms where I've got infinity in the denominator, I'm going to make the claim that they tend towards 0. A small modest number divided by an infinite value goes to 0 basically. And that equals now negative square root of 2 plus 0 over 3 plus 0, which is going to give us the value of negative square root of 2 divided by 3. And that denominator is already rationalized, and that completes our limit. Thank you for joining for these 5 examples of finding the limits of rational or radical functions analytically. See you soon.